All right, so this is just a video going through the solutions from the worksheet so that if you have any questions, it hopefully will clarify any issues that you might have and help you with any rearranging issues if there are rearranging issues, but just kind of walk you through my process and give you a few extra examples beyond those that were in the original PowerPoint. So you can skip ahead to just the questions that you're wanting to know about or whatever it is that you happen to need. So first question is, an Olympic class sprinter starts a race with an acceleration of 4.5 meters per second squared. What is her speed 2.40 seconds later? And then B, how far is she from the start after 2.40 seconds? So first of all, I like to go through the question and list the variables. So a sprinter starts a race. So at the start of the race, how fast is she going? Well, at the start of a race, you start your speed out at 0. So initial speed at the beginning, even though it doesn't tell us, V0 is going to be equal to 0 meters per second. All right. She starts the race. She has an acceleration of 4.5. So we have acceleration of 4.50 meters per second squared. What is her speed? So we're looking for speed 2.4 seconds later. So I'm looking for a second speed. That's what I want to find. And my time is 2.4 seconds. Okay, so now that I have this, so this is all the information for A. So now that I have all of that information, I'm going to check my equations and figure out, well, which of these equations uses V0, V, T, and A. So looking here, V0, that's what I'm looking for. I have this, I have this, I have this. So that's the ideal equation. The rest of them all use D in it. So velocity is equal to V0 plus AT. This is a nice, easy question to start with. 0 meters per second plus 4.5 meters per second squared times 2.40 seconds leaves us with a velocity. So putting that in your calculator, you will get a velocity of 10.8 meters per second. So that's her velocity after 2.40 seconds. You'll notice I've done 10.8 because each place in the question we have 3 significant digits. So we've got 3 digits in each, so we're going to say 3 digits at the end. B, we have very much the same information, but it says how far. So now for B, I'm looking for what is D. So what I'm going to suggest is when you're looking for D, if possible, try to avoid what you've calculated. There are some times when you're going to have to use a calculated piece of information in order to solve for something else. But I'm going to choose the 3 pieces that were originally given to us to calculate D because I know there's no calculation errors in them. So that's the only reason for that. And it gives you some practice with some other equations. So I want an equation for D that does not include V. So I want V0, A, T, and D. So if I look here, D, V0, T was given to me, A was given to me, and T2 is, or the second T is just the same T you have at the beginning. So again, this is one we don't have to rearrange because it's in D equals, and we want to find D. So V0 T plus half AT squared. Putting into our equation, 0 times 2.40 plus, should leave my units in there, plus half. So this is just going to go to 0. It's not going to matter anyway. A is 4.50 meters per second squared times a time of 2.40 seconds. Okay, multiplying those 3 pieces together. So this one's just going to be equal to 0. 0 times anything is 0, so we can just get rid of that term. And we're going to have half times 4.5 times 2.4. And we better throw the squared in here. If we drop that, that's going to cause us trouble. So putting that all in your calculator, make sure you follow order of operations. So this should be squared first. and then multiplied by the original pieces. Most scientific calculators will keep track of that for you if you just type it in the way it's shown. You will get 12.96 meters. Again, we have 3 significant figures everywhere, so we would say, well, that's 13.0. This 6 is going to cause the 9 to go up. We keep the 0 to show 3 sig figs. So distance or displacement is equal to 13 meters. And I use the word displacement specifically because we said if we're using velocity, we're going to get displacement, which is a vector, rather than distance, which is a speed. Okay, and you'll notice in some of the questions, and this is, our books do the same thing. So many times we use to mention speed and velocity will often kind of get interchanged. So we're given speed here. We can use the same equations, and perhaps we just don't know which direction the individual was moving. Question 2, freight trains can produce only relatively small accelerations and decelerations, which makes sense because they're heavy. We're going to get to that when we look at Newton's laws. A, what's the final velocity of a freight train that accelerates at a rate of 0.05 meters per second squared for 8 minutes and starting with an initial velocity of 4 meters per second? So again, let's list our variables. I'm going to try this question is a little longer, so I'm going to try to keep things fairly organized so it all fits in. So we list our variables. We have an initial velocity. Initial velocity is 4. We want to know what is the final velocity. So that's what we're looking for. We also have an acceleration, and it's speeding up. So increasing speeds, we're going to leave it as positive, 0.0500. And meters per second squared. And time is equal to 8 minutes. We'll have to zero off, but we'll throw it back in later. So if you look through these equations, you'll notice meters per second, and we have minutes. We need to turn this minutes into seconds. So we're going to multiply by 60 and we get 480. You'll notice that 0 is going to be a significant 0. So 480 seconds. Now we're going to put it into our equation. So which equation will give us B, knowing B naught, A, and T? It's going to be equation 1. So we'll use that. Velocity is equal to B naught plus AT. Substituting in, we get 4.00 meters per second. Let me adjust here. Plus an acceleration of 0.500 meters per second squared. And that should be another 0 in front. We'll squeeze that in. So 0.005 and 0.05 rather. And then our time is going to be 480. Putting all of that into your calculator, the train is going to have a final velocity of 28 meters per second. If you're not getting 28 meters per second, double check what you put in. Did you use seconds, minutes instead of seconds, or did you forget to follow a order of operations, which means multiply first and then add? Like I said, most scientific calculators will keep that straight if you just put it in the order that you have to, in the order that the question's given, it'll automatically sort. All right, so that's the first one. We'll throw a line in here. So that's A. B says, okay, if the train can slow down at 0.55 meters per second squared, how long will it take to come to a stop from this velocity? So now we got a second question. We need to know the starting velocity, final velocity. I want an acceleration, and it doesn't say anything about distance in B, but it does give us some time information. So initial velocity, we're starting from the original speed, so 28 meters per second. It's coming to a stop. Stop means we have 0 meters per second when we finish. Slowing down means that this is going to be negative. So negative acceleration of 0.550. If you don't miss that negative, we're going to end up with some trouble. So meters per second squared, and then our time is what we're looking for. Again, we're going to use exactly the same formula. So for this one, we have V equals V naught plus AT. Substitute in 0 is equal to 28 plus our acceleration is negative 0.550 t. Rearranging. These two are connected. We can't move them yet, so we're going to move the 28 first. So minus 28 minus 28. So we're undoing the addition first. So that leaves us with negative 28 equals, so those cancel out, negative 0.550 t. Dividing both sides by negative 0.550 leaves us with t equal to, those cancel, t is equal to, I wrote the number down, 50.9 seconds. Okay. If you didn't write your units in, like I skipped writing the units in here for the sake of space, if you did not write the units in, what you might find you need to do is look back at the original units. If originally in the question you had meters for lengths and seconds for times, you know for sure that this time should be equal to seconds. So that's going to be 50.9. Now I'm going to go back and I'm going to plug a couple pieces in here that we were looking for, and I'm going to erase the original part of the question because I want to be able to do D. So just give me give me a second here. Here we go. I'm just going to grab the eraser and we'll get rid of a little bit. This is maybe not the fastest way to do this. So the second part of the question says, how far will it travel in each case? So what I'm doing is I'm just keeping the variables from the answers from A and B in the list of what we know already in the question. Then we're just going to throw in one extra variable and we're going to see, well, what would it take to solve for D, the displacement or the distance? All right, so now that we have some space to calculate, let's grab our pen again. And here, now part C gives us, okay, so distance for A or displacement for A. So in that case, we have these 4 pieces of information. Now we calculated that velocity. Because we calculated the velocity for A, I would suggest using an equation that doesn't have A. So this would be the best equation to calculate distance for part A, because there's nothing calculated in this question. Everything was previously known. So we'll use that equation to do this one. Distance is equal to 1/2. V naught is the original speed, so 4 meters per second, plus the final, which is 28, times the amount of time it takes, 480. And putting all of that into your calculator, you will get that you have traveled. I'm going to just do a quick question. I used another formula when I calculated, and I always like cross-referencing. So 0.5 times 32, that's 4 plus 28 times 480. I get the same answer both ways. I guess the answer is from the answer key. We're looking for distance. The distances were all put in meters, so we're going to put meters in for our answer. Okay, so that's the distance in case A. Distance for B. So if I want to know the distance for B, we have 2 velocities and an acceleration. We can use a couple of different formulas. We could use this one. We could use this one. It really doesn't matter. if you're not sure if your time was calculated correct, I would use equation 3. But if you know your time was calculated correctly, you can use this one or this one. It saves you rearranging. So let's just use the same equation we used. Actually, I'll use the equation that I selected. It's funny how one time you do it, you pick one equation, another time you choose another. But the equation I chose to use was this equation. So I said, well, D is equal to V naught T plus 1/2 AT squared. And I could have used that back in the original. All right. So what are we doing to calculate? So distance equals V naught is 28 times a time of 50.9 plus 1/2 0.55. Make sure you keep the negative, and 50.9. I'm running out of space. I think we're going to need to rewrite. Sorry about that. One of the arts that I have yet to master is spacing on slides unless I map everything out before, which is one of the reasons why it takes me so long to sometimes get recordings done, is because I print them out and then I handwrite everything on them, and then I record at least once, maybe twice. So initial velocity was 28 meters per second times 50.9 plus half negative 0.55 times 50.9. Even then I'm short on space. Just plugging all of that into your, and that's going to be squared at the end. Now, putting all of that into your calculator, you should get a distance that is equal to 713 meters. Okay, so it takes much longer for it to speed up than it does for it to slow down and come to a stop. All right, next question. This one's a little shorter for us. A fireworks shell is accelerated from rest to a velocity of 65 meters per second over a distance of 0.25 meters. How long did the acceleration last? And then calculate the acceleration. Now, as you read the question, there's some information. When you see the word rest, if something is at rest, you know that the speed of it is 0 meters per second. So let's list our variables. Initial velocity. Velocity at time 0 is 0 meters per second. Final velocity is equal to 65. Distance equals 0.250. And we want to know time. So there's all of our pieces. So first of all, which equation do we have that has all 4 of these pieces in it? Well, if we look through our equation, our last equation does not have acceleration, but we can choose that one. So distance equals half V naught plus V. Now these are equations that I would never expect you to memorize, but you just have to be able to select them. So it makes sense that firework is not going to accelerate for very long, so we can expect some small numbers. So the distance is 0.250 meters. Everything is in meters and seconds, we don't have to convert, equals half. Initial velocity is 0 plus 65 meters per second times the time. So now that we have that, let's simplify. 0.250 meters is equal to 0 plus 65 is just 65. So half times 65 leaves us with 32.5 times time. And then we're going to divide both sides by 32.5. Now, if you do a unit analysis, you'll be able to prove that meters divided by meters per second gives you time in seconds, but I'm not going to require that for you. So we get a time of 0.00769 seconds. And you'll see the answer key gives you the answer in scientific notation. So if we move our decimal 1, 2, 3 places, we would get 7.69 times 10 to the negative 3 seconds. So it's exactly the same information. So those are two ways to express the same answer. Now the question, so that's A. Now the question says, well, what's B? So for B, we're going to see if we can squeeze it in this little tiny space. Calculate the acceleration. So I know time. I want to find what is A. So is there an equation that uses this information that would let me calculate A? Well, I'm going to suggest let's skip the term with T, because what if you screwed up your scientific notation? Let's choose this equation for solving for acceleration. So for B, we're going to say V squared equals V naught squared plus 2AD. Put all of our information in. This could get a little bit tight. So velocity squared is 65. I'm going to leave the units out just to make a little less space. Equals 0 squared is just 0 plus 2 times the acceleration. Let me erase here. I want to put just A instead of a bracket. And then our distance of 0.250. All right, so 65 squared leaves us with 4,225 is equal to 2 times 0.25 gives me 0.5A. And then we're going to divide both sides by 0.5. They cancel, and the acceleration is equal to 8,450 meters per second squared. That's a wildly fast acceleration. But for a small object that's being launched into the air, perhaps is not unrealistic. It's not a question I've made up, so I don't know the specs. Question 4, a car skids to a stop trying to avoid hitting a deer. The car skids 21 meters in 2.3 seconds. How fast was the car going originally? So again, I take a minute and list all the information I'm given in the question. Car skids to a stop. That's 0 meters per second. So I know eventually it's going to have a velocity of 0 meters per second. It goes 21 meters. And it took 2.3 seconds. And I want to know how fast was the car going at the beginning. So there's all of my information. So if we look through our equation, we have no acceleration in this question. So we are going to use equation 4. Distance equals 1/2 V naught, which is our original that we're looking for, plus 0. Oops, let me throw, I'm using variables, I'll use all variables rather than flipping back and forth. So V naught plus V times T. Let's substitute in. So 21, so everything's in meters and seconds, so we're good. So 21 is equal to 1/2. V naught is going to be what we're looking for, so we'll leave that plus 0 times 2.3. Okay, so now that we have that, let's simplify things a little further. So 21 is equal to, we can put the 1/2 and the 2.3 together. So if we put the 1/2 and the 2.3, we are going to get 1.15. So those two can get, because we multiply in any order. And then inside here, we'll simplify and we just get V naught. Divide both sides by 1.15. And we get the final velocity, or the initial velocity, rather, was 21 divided by 1.15 18.2, actually 18.26. So that's going to be 18, I'll say 18.26. And if we round, so I'm just leaving some extra decimals, you'll notice 2 sig figs, 2 sig figs. So if we round to 2, that's 18 meters per second. Using proper rounding. So pretty easy. A little more rearranging in that one, but again, it's always great when one of the velocities is 0 because it simplifies the question quite a bit. Question 5, what is the final velocity of a car that starts from rest? So again, we have this 0 meters per second and accelerates at 3.90 meters per second squared for a distance of 100 meters. For the purposes of this question, assume that the 100 meters has 3 sig figs. I can't do the proper notation in the computer as far as I know. Maybe I can, and I just don't know how. And I haven't used scientific notation here. So we'll assume that we have 3 significant figures for this question, and I'll work on editing it later to throw a 0 on the end and change the sig figs. All right, so what is the final velocity? I'm looking for V. We might as well list that now. Of a car that starts from rest, there's V naught equals 0. And accelerates at 3.9 meters per second, so it's speeding up. For a distance of 100 meters. So there's all of our information. Now all we need to do is select which equation we're going to use. So we need an equation that uses velocity, acceleration, and distance. And that's going to be the third equation that's on our list. So now we can substitute in. So let's write our equation down. First, I always like to start with the original equation. I find it helps you just make sure you're lining up all the information in the right spot. So we're looking for velocity, so we're going to leave that. Equals V naught squared is just going to be 0 plus 2 times 3.9 times 100. Simplifying, V squared is equal to 2 times 3.9 times 100. Putting those 3 into the calculator, we get 780. And then we take the square root of both sides because we want to find just V. Square root of 780 leaves me with 27.9 meters per second. So that's going to be our final velocity. Little rearranging, not overly complicated. It's really pretty simple algebra. All right. Now this question is a little bit of a challenge question. So if you're looking at it kind of scratching your head, it's probably because you haven't done a physics course or it's just been a long time since you've done a physics course. Sometimes even when we've done these courses or when you've taught the questions before, sometimes you get a question, you'll read it again, and you go, wait a second, how am I going to do this question? I had one of those moments today and I'm not sure. Not exactly sure why, but anyway, we'll call it a brain fart. So we want to list our variables. So we'll go through our question and I'm just going to list and we'll pull out each of the information. It's a long question, so I'm assuming I need everything. A hockey puck slides across the ice with an initial velocity of 7.2 meters per second. It has a deceleration, so it's slowing down, of negative 1.1. The negative's not there, but we assume it because it says it's decelerating. Decelerating at 1.1 meters per second squared and is traveling towards a, oops, I've written that in the wrong spot. It's traveling towards a goal 5 meters away. Let's get these in the right spots. We have negative 1.1 meters per second squared and distance is equal to 5.0 meters. How much time does the goalie have to stop the puck? So based on what we are given in this question, if you look through it, we need to find time. We only have initial velocity, acceleration, and distance. So if we go through this question list here, this one has final velocity, can't use that. This one I could use, but one of our issues is you'll notice it's got t in the question twice. And when there's time in the question twice, especially like this, it's a bit of a pain to solve. If you're familiar with the quadratic equation, we could rearrange it and use the quadratic equation to solve for t. But again, it's extra complicated, extra work. So we're going to take an easier route. If we knew how fast it was going, if we knew this piece of information, when it hit the net, we could figure out how long it takes. Can you find, just using this information, can you find v first? And then we'll find t. So let's look at our equation. So we'll get rid of this lovely check mark here. We're not going to use that one because it's complex. We'll say it works, but hard. Okay, so we're going to skip that one. We don't want to use it because it works, but it's complicated to rearrange. Nobody likes rearranging more than necessary. So what can we use using this information to find v? Well, if I look, this one uses final velocity, initial velocity, acceleration, and distance. So I'll use this equation to find velocity first. So this is a two-step question. Velocity is equal to initial squared plus 2ad. Substituting in, we're looking for a final velocity, is equal to, our initial velocity is 7.2 meters per second, plus 2 times the acceleration of negative 1.1, don't forget that negative sign, times our distance. Oops, helps if I actually put the distance instead of the letter, times 5.0 meters. All right, I've left some units out just because I've run out of space if I don't. So velocity squared is going to be equal to, put all of this in your calculator, follow order of operations, make sure you're doing the multiplying first and then adding together. But most of you have a scientific calculator that will allow you to do that in one step. It'll automatically track it. And see, do you get the same information I get? I get 40.8 meters. Oh, it's going to be meters squared per second squared. I'm going to leave, whoops. I'm going to leave that off for the time being. And if you'll notice, I just added my square in. I forgot to copy a square. So I added my square in here if you were copying along. Okay, square root of both sides to get v. Velocity is equal to 6.3 meters per second. Okay, now that we have that, now find t. Find it with an easy equation. And the equation I would pick, oh, this one's a pretty darn good one for me. So velocity equals v naught plus at. Okay, velocity 6.3 is equal to 7.2 plus negative 1.1 times t. Order of operations says we can't separate these as long as there's adding, so we're going to move this 7.2. Move it to the other side, subtract 7.2. 6.3 minus 7.2 leaves us with negative 0.9 equals negative 1.1 t divided by negative 1.1. T is equal to 0.81 seconds. Now, if you were checking the answers at the bottom of the page, it's possible you may not have got the same answer as this one. I did update answers as I was going along, but I don't think I updated it online. So if you don't have 0.81 on your answer key, my apologies. We'll try to get the right files loaded in shortly. shortly. All right, so two-step question, a little harder to identify because it doesn't tell you which order to calculate in. Typically, I would ask calculate velocity and then calculate time to help scaffold you to get the right information in the right order. Question 7, if a moose can accelerate at 21 meters per second squared from rest, how much time will it take to accelerate to a speed of 4 kilometers per hour? This is really a nice, easy question. There's only one little glitch in it, and the biggest issue is we've got kilometers per hour and meters per second. So this is questions really nothing more than a reminder to change units. So we're going to start out with, we have an acceleration of 2.1 meters per second squared. How much it's starting from rest. So initial velocity is 0. How long will it take to get to a speed? So our final speed is 4 kilometers per hour, and we want to know t. So the biggest thing is we need to convert velocity. So let's multiply by, get rid of kilometers, multiply 1,000, and then we want to turn the hours into seconds. So we're going to end up dividing by 3.6. Okay. Leaves us with, I always second guess when a number is a duplicate, just because I'm always afraid we've got one sig fig here. So we'll go with 1.1. I'll keep one extra just for the sake of rounding. So 1.1 meters per second. So that's going to be our velocity that we use now. So now I need a question that uses all this information and will allow me to find t, and the equation that we'll use is the very first one. Velocity equals v naught plus at. So velocity is the 1.1 meters per second is equal to 0 plus an acceleration of 2.1 meters per second squared times time. 1.1 meters per second is equal to 2.1 meters per second squared times time, divide both sides by 2.1. Equals time. 1.1 divided by 2.1 is 0.52 seconds, or approximately 0.5 seconds. I won't it'll be too hard on you for sig figs on this one. I think I may actually add an extra sig fig on that acceleration. All right. Question 8 is the hardest question of them all. It's the very last question. Some years I'll say omit it, but it's a good question. And I'm going to make a diagram with this one, this particular one first, because I think it helps to tell the story, and it'll help you visualize maybe what's happening. So put yourself in a vehicle. When you try to stop your car in an emergency, there's some time before you can react. So we call this reaction time. It's one of the reasons for the 2-second rule between vehicles, especially important in the wintertime, so that you have time to react and the road has time to be slippery. Your car is going 25 meters per second and your reaction time is 0.2 seconds. Then after you hit your brakes, it decelerates at 9.5 meters per second squared. How far will, I'm not sure why hours in there, will the car travel before it stops? Looks like we got a typo in there. How far will the car travel before it stops? All right, so the first thing, let's kind of visualize the scenario, and I'm going to do it with a graph. So I'm going to put speed over here, and I'm going to put time here. So you're driving down the road, and you start at 25 meters per second. Okay, you're driving down the road at 25 meters per second. After 20 seconds, or 0.2 seconds, you hit the brakes. Then you start to slow down and you eventually stop. So this is a two-part question. So the word then tells me that I've got two parts. Okay, so for the first part, we'll call it our reaction time. Okay, so the first part is our reaction time. How long is it going to take us to stop? So our reaction time, acceleration equals 0, or we're going at a constant speed. If there is no acceleration, then velocity is equal to distance divided by time. Okay, because there's no acceleration. I'm not slowing down yet because my brain is still processing. It needs to hit the brakes, but it hasn't done it yet. So we're going to substitute some information in. We've started out at a speed of 25 meters per second. How far does it go? That's my D, while I think. That thinking time is 0.20 seconds. Okay? So we have our velocity is 25. Our time is 0.2. And our acceleration is equal to 0. Now, how could we prove that? What if you go, I don't know if I'll ever remember that. Look at this equation. Okay? If we take this particular equation, we say acceleration is 0. 0 times anything means that's going to go away. So we're going to get distance is velocity times time. Well, look at what happens here. Multiply both sides by 0.2, I get distance is equal to 25, which is my velocity, times time, which is 0.2. It is this equation, but you're just not told you're decelerating. You're not accelerating or not decelerating there. It's one of those things that's implied from experience. So that's what makes this question a challenge question. So 25 times 0.2 leaves us with 5 meters. Okay? So that's our reaction time, part 1. This is the think time. Okay, part 2. So this one is 5 meters that we've gone there. Squeeze that in. So, okay, how far do I go in this section of the curve? This section of the graphs, the time when I'm actually slowing down. So now I've hit my brakes, I'm slowing down. What about then? Well, we know initially our velocity started out, it's still 25 because my foot hasn't come off, is just touching the brake. We don't know how long it's taking us because it doesn't tell us how long it takes to actually slow down. But we do know we accelerate or decelerate at negative, because we're slowing down, 9.5 meters per second squared. And we also know that, so we got velocity, we have acceleration. We also know that it comes to rest. So our initial velocity, our final velocity is going to be equal to 0 meters per second. And I want to know what is the distance. So let's look for an equation that does not use time in the second half, because we only know the time for the first half. And that equation will be this one. Okay, bring that equation down here. So velocity squared is initial velocity squared plus 2AD. So 0 is equal to 25 squared plus 2. The velocity is negative, so don't forget that negative 9.5. I almost threatened to quit university a few times over negative signs that I missed that made physics questions not work right. So make sure you keep them. So 0 equals 25 squared plus all of this. So 0 is equal to 25 squared gives me 625 plus 2 times 9.5 gives me 19, negative 19 times d. Let's rearrange. Minus 625, minus 625. So running out of space. So we get negative 625 equals negative 19d divide by negative 119, both sides, and D equals 33 meters. So the total, so this, in this section, so the total is equal to 5 meters plus 33 meters, gives me a grand total of 38 meters of stopping distance. And that's our final answer. So this is another one of those, kind of like the PUP question, where it's a two-part question, and yet it's not really obvious that it's a two-part, but that then word is a really good clue that you have two parts in this question. Again, if I was giving you a question like this on an assessment, I will often scaffold it so that you know you're calculating in two parts. You'll have A and you'll have B. Now, my instructors were not that kind to me, but because of the rate at which we go through information, the fact that we don't have 2 or 3 days per topic to just kind of sit on them and practice them a dozen times, we'll give you a little extra scaffolding in there so that you still get to manipulate the concept. So this is really good practice for doing algebra and all of that stuff. So let me know if you have any questions. Otherwise, hopefully that helped to clarify some of the questions you may have had while you were working on the worksheet.